Okay, thank you for the invitation. So I'm going to talk about weighted Hodge ideals and what I will try to show you. And so the way I think about weighted Hodge ideals is like a generalization of multiplier ideals and the adjoint ideal. So let me first start talking a little bit about those and then try to convince you that these are generalizations. So throughout the complex, X will be a smooth complex variety. And usually, I'll try to be consistent with the notation. D will be an effective reduced divisor. Okay, so let me start talking about these two objects I named, which are very important in birational geometry. So multiplier ideals associated to a pair, in this case, we can talk about a multiplier ideal of a Q divisor. It doesn't need to be a reduced divisor. Uh, is defined in the following way. So we define, let's say, the multiplier ideal x comma d prime to be the push forward of this sheaf. So how do I write it? Okay. So it's this formula where f is a log resolution of singularities. So the formula is not very important. The point is that associated to a Q divisor inside the smooth variety, we can associate a sheaf of ideals. Okay. And for instance, the main or the common example is, let's say, when we are working on A2, so that a sheaf of ideals is like a true ideal. And if we have the divisor, the cuspidal curve, so this is a well-known example. And in this case, associated to the Q divisor CD, we have that this is the trivial ideal. If C is between 0 and 5 over 6, and if you are between 5 over 6 and 1, this is the maximal ideal at the origin. Okay, so this is the first, this is one of the first examples you learn when you're talking about multiplier ideals. So this should be multiplier ideals. Okay, the other ideal I'm going to talk about is the adjoint ideal. This is of a pair when D is now a reduced divisor and is defined in a very similar way. Is the push forward of this relative canonical. And now we add, we have this formula. Again, this is a sheaf of ideals. So the formula is very related with the multiplier ideal. And in this case, if we look at the cuspidal curve, the adjoint ideal is also the maximal ideal at the origin. Now, what do these ideals capture? So let me make this remark.
What is detailed?
Sorry? Oh,
Detailed.
sorry. So the tilde is the strict transform of D. So if you want, the pullback of D consists of this D tilde and a bunch of exceptional divisors, right? So D tilde is a smooth variety, and if you restrict them up to D tilde, this is a resolution of singularities of D. Okay, so first we have that the pair is log canonical. If and only if this multiplier ideal for a is trivial, and here epsilon is a small number. Okay, So these multiplier ideas are capturing these kinds of singularities. And the other thing it captures is that the pair is normal and has rational singularities and has rational singularities if and only if the adjoint ideal is trivial. So in some sense, this multiplier ideal, when you have d multiplied by a number very close to 1, captures how long you are from being log canonical, and the adjoint ideal captures how far you are from having rational singularities. And these two ideals are very important, like in the classical theory of birational geometry. They have been used for different kinds of applications. And let me just give you one property it's satisfied in the same flavor that the final geometric application I will show about weighted Hodge ideals. Okay, so it says the following: suppose that you have a finite set in projective space, and you can find a hypersurface in Pn of degree d, such that on each of the points on S, the hypersurface has high multiplicity. Okay, so this means that the multiplicity at the point is larger or equal than k, where x is a point in S for, so let's say for all x in S, it's a finite set. Then the conclusion, I mean, using multiplier ideals, we can find if these multiplicities are high enough, we can find a hypersurface that of lower degree that contains all of these points. Okay, so this is the kind of geometric things you can do. So then S lies in a hypersurface of degree smaller or equal than the round down of dn divided by k. Okay, so here is clear. If we can construct a hypersurface on which all of the points have high multiplicity, then we can find a hypersurface of small degree that contains all of the points. And this is a common procedure in the application of multiplier ideals. In general, these hypersurfaces are not too hard to find. But okay, so this is the motivation of I mean, this is like the story of these kinds of ideals. And now let me start talking about now Hodge ideals and weighted Hodge ideals, and then I'll connect with these ideals I started talking about. Okay, so now how does the story of Hodge ideals start?
But there is no restriction on the cardinality of S, no?
No restriction. It has to be finite. So let's say here, finite. But yeah. Okay, so I'm going to use this notation. This is the sheaf of meromorphic functions with poles along a divisor D. Okay, so remember X is a smooth variety and these are reduced divisor. One way of writing this is as the union of these coherent sheaves corresponding to, yeah. Mm. Mm. Actually, I'm not sure. So the question is, if you have this finite set of points, if this is the modest degree you can find where you can fit all of this. No, I don't think it's sharp because I think if you start imposing conditions of these points, then you can find like something of lower degree. Well, this works for any set of points of these points. So yeah, I don't think it can be sharp. But this works for any set of points. That's like the nice thing. Okay, so this is the sheaf of, okay, so I said meromorphic functions with poles along D, right? And like the key point is that it has a dx module structure. Okay, So this is one of the first interesting modules. It's like the localization along a divisor. And moreover, via the Riemann-Hilbert correspondence, it corresponds to, let's say that we have the inclusion of U, which is the complement of D, into X. This corresponds to, so what notation should I use for perverse shifts? Rj lower star Q U N. Okay. And then not only because it corresponds, but because this sheaf has very nice properties, the key point is that it underlies a mixed Hodge module. Okay. So I truly don't want to spend any time explaining what goes under being a mixed Hodge module. Is a pair of a D module and a perverse sheaf, such that many properties are satisfied. But instead, I'm going to show you, I'm going to just name some properties that follow from the fact that it is a mixed Hodge module. And probably the most interesting one for this talk is that it has a Hodge filtration. Okay, it is endowed with a Hodge filtration. That we're going to use this notation, F bullet OX star D. And this, each FP OX star D is a coherent module, a coherent OX module. And one fundamental result from Saito is that each degree, FP OX star D, is contained in what's called the pole order filtration, which is just functions with a pole of order p plus 1. Okay. Now, the idea of, studying Hodge ideals corresponds to study the Hodge filtration of this sheaf. And this has been studied by Mustaza and Popa and some other people. And like the key point is that what they realize is that studying this Hodge filtration, to study this Hodge filtration is actually a better idea to study how these two filtrations differ. Okay. Like measuring, trying to understand how different is the Hodge filtration from the pole order filtration. And then if you look at these containers, this is the same as the definition of the Hodge ideals in the following way. So this is the definition of Hodge ideals. So this being contained here is essentially the same as having a formula of FP OX star D is OX P plus 1D times an ideal. Okay, so being contained is essentially this formula, and these ideals are called the Pth Hodge ideals. Okay, so as I said, it has been vastly studied by Mustaza and Popa, by Saito has some results, and many people have been studying this. For instance, if the Hodge filtration coincides with the pole order filtration, then this means that the divisor is smooth. And there are many other ways of relating the singularities of D with these Hodge ideals. Okay, so this has been a vast project which has been extended to Q divisor. Very recently, this has been extended not to a hypersurface but to higher codimension. So it's like a big ongoing project. But I want to talk about a refinement of these Hodge ideals, which are the weighted Hodge ideals. The idea is that part of being a mixed Hodge module is that you had that Hodge filtration, but like the mixed part means that OX star D is also endowed with a weight filtration.
Sebastian, maybe just a question if I understood well. Going back to this Griffiths result, if the ambient space is Pn and D is smooth hypersurface, So the Hodge ideal is something trivial then, as far as I see. So,
Yes, if you have a smooth hypersurface, all of the Hodge ideas are going to be trivial. Yes,
okay.
and it's an if and only if. So with a weight filtration, so in this case we use the notation W bullet OX star D, but this is a filtration by sub DX modules. Okay, so now instead of studying the Hodge filtration of OX star D, the plan is to study the Hodge filtration of each of these sub DX modules. And this gives rise to the definition of, okay, so let me add that if I take the Hodge filtration of a piece of OX star D, so now here I'm writing the weight n plus L because the lowest possible weight is weight n and the highest possible weight is weight 2n. So I just write it as n plus L. This by definition is contained in FPOX star D, which as we said is contained in OX P plus 1 D. So we can just like mimic the definition of Hodge ideals, and we have that FP weight n plus L OX star D must be OX P plus 1D times an ideal that we call IP weight LD. And this is the weighted Hodge ideal. Hodge ideal. So we can say the ELF weighted Pth Hodge ideal or something like that. But it is that it has two indices. And now the idea is, for the rest of the talk, I'm going to like present some results about these Hodge ideals, and then my hope is to end up with a geometric result, combining all of these different local and global results that mimic what you can do with the original ideals in birational geometry.
I mean, last time I read about the mixed Hodge modules, was a long time ago. Is it possible to define FP and this W in a simple way in this context? This Hodge filtration, because
Actually, no. In general, like the reason of the kind of the death of the result of Hodge ideals is that it is hard in general to describe. Uh, to
no,
describe.
I am saying that the Hodge filtration itself, this FP that you are writing.
Yeah, no. So that in general, it's not that easy. Like I'm going to give one result later in which, if you use the V filtration, then you can give an explicit description of them. But then the question is, how explicit is the V filtration for you, right? Finding in general the V filtration is also hard. So
Okay.
Okay, so let me first give an easy way of describing the zeroth piece of the zeroth Hodge ideals. So the birational definition of I0 weight L. So these are called, or I call them weighted multiplier ideals, and there's like a separate paper studying this. And the result is that if we have a log resolution of singularities of xd, and we call E to be the reduced preimage of D, okay? So in some sense, it has the D tilde, the one that is birational to D, plus a bunch of exceptional divisors, and we counted with multiplicity 1 here. Then we can define these zeroth Hodge ideals just by pushing forward these studied shifts. So let me just say this. When you study the P forms with log poles, right? Like the sheaves omega P Y log E, this has a weight filtration, which comes by the number of divisors on which you have a pole, right? This is essentially what goes into, if you have a smooth variety, then you look at the cohomology, it has a mixed Hodge structure, right? And the weight piece of the mixed Hodge structure comes exactly from the weighted pieces of these of these sheaves of log poles. The top one, like omega n log e, is exactly the omega y e, right? And then this is the weight I mean here. So in some sense, this is an explicit, if you may, way of describing these Hodge ideals. And maybe this is a result of Saito. You have that if you push this whole sheaf, omega ye, this is omega xd tensor with the sheaf I0d. Okay? But if you remember the definition of multiplier ideals, this is essentially the definition of 1 minus epsilon d. Okay? Tensor omega xd. So the remark is that I0 is a known sheaf, which is this multiplier ideal. Okay, so that's the first part. And the second part, so this is a theorem, is that I0 weight 1 D is the adjoint ideal. Okay, this is an easy result. And so it was somehow hinted by Budur Saito and some work of Budur, but in this way of having like this I mean, Budur Saito hinted this relation between weight n plus 1 and the adjoint ideal. But in this way, so this is a result that appeared in my paper. So, okay. So this is, okay, these are the two first results. So let me conclude this part by saying that all weighted Hodge ideals form a chain, okay? So let's say we start, so in general, we have this, okay, we have weight 0D contained in IP weight 1D. And as I said, this goes up until IP weight ND, and as the weight goes up until 2n, this is forced to be IPD. So what do we have? This is always a very not interesting divisor, ideal, because this is just the ideal sheaf of P plus 1D. Okay, so this captures nothing about the singularities of T. So in some sense, we ignore this part, and then we have this chain of ideals. Okay. Now, if P equals to 0, what we have described is that the leftmost part is the adjoint ideal, and the rightmost part is this multiplier ideal that is above. Okay. So the rest of these weighted Hodge ideals for P equals 0 are like a refinement of these two ideals on the extreme. And for higher P, these are going to be generalizations of these two ideals, okay? And somehow this can be made more precise. And if I have time, I'm going to talk about it.
In Saito's result, it is for any small epsilon, no? Or
yeah, so this is, sorry, this is for epsilon. Okay, so this is my justification of the fact that weighted Hodge ideals are first a refinement of Hodge ideals, and second a generalization of multiplier ideals and adjoint ideals. Okay, so as I was saying to Hossein, studying the Hodge filtration is in general hard, and giving explicit descriptions is in general not easy. So one thing we can attempt with weighted multiplier ideals is, instead of describing each of them, you can describe how much does it grow at each of the steps. Okay, like describing the jumps. If you can understand these jumps, in the end you will understand. I don't know, if you can understand one of, like, probably the lower stream, then you have some hope of saying something about the Hodge filtration. And that's the next result: how to describe these jumps in terms of known numbers. In the case of isolated singularities, okay? So the first thing you can see is that you always have a short exact sequence of this sort that just comes from the definition of a weight filtration. So if you have this quotient, this is by definition what we call the GER of weight m plus L, OX star D, right? And now if you take the Hodge piece, the pth Hodge piece, all of this is strict. So what you obtain here is P plus 1D tensor IP weight L minus 1D going to weight P plus 1D tensor IP weight LD. And then this is just what it is, FP of the same thing, right? So FP of this thing is what is capturing these jumps on these Hodge deals. And an important remark is that if L is larger or equal than 2, then ker m plus L, OX star D, is supported on the singular locus of D. So for instance, if D has isolated singularities, these are going to be skyscraper sheaves. So we can think of them as vector spaces, and we want to describe the dimension of them as vector spaces. Okay. So I'm going to
But
write.
there might be singularities which even not supported there, no? I mean, not all singularities, over all singularities, there will be skyscraper.
Exactly. Yeah. Yeah. So that's important for the geometric description I'm going to give in the end. Yeah. Exactly. Which are the ones showing up, and what's the dimension on them is an important information of the singularity. Okay, so I don't want to say too much about what I'm going to write next. So let's say x in D is the only isolated singularity. Okay, just to simplify. If you have isolated singularities, you can take an open set, exclude the others, and let's focus on one. And one thing you could see is that, how should I write this? Okay, let me just write here. Okay, in this case, what we would have is that GER m plus L W OX star D, just to simplify notation, it's going to be the push forward as a D module of some vector space that we're going to call HL. Okay, and HL is not only a vector space; it has to be a pure Hodge structure, right? We have a pure Hodge module on the left, so it has to underlie it has to be a pure Hodge structure. And then what we're looking at, the dimension of FP of I plus HL. You look at the definition, you unravel all of this, and what I'm going to write is really not important. All I want to conclude from this is that if you want to compute these dimensions, what you actually care about is this piece, okay? If you know each of the dimensions of the GER pieces of these pure Hodge structures, you obtain all of these things, right? So instead of computing the dimension, the result I'm going to give is how to compute these dimensions of the Hodge pieces of these pure Hodge structures. And then there are many ways of thinking about this, but I want to have a birational approach. And the first result is that now suppose you have a resolution of singularities of D. Any resolution of singularities, I mean a log resolution, so that the exceptional set is a simple normal crossings divisor that is an isomorphism outside of X. And let's call G the exceptional set, the exceptional divisor, which is a simple number crossings divisor. Then we can describe these dimensions explicitly in terms of G n minus P HL. Then this is going to be, okay, so G is now an n minus 2 dimensional variety. As it is an algebraic variety, it carries a mixed Hodge structure. So I'm going to use this notation for the Hodge pieces of that mixed Hodge structure. So here I'm looking at the middle cohomology of G, and then I'm looking at the Hodge pieces of this mixed Hodge structure. So this is true if L is larger or equal than 3. And in the case of L equals 2, there is a correction term, which is P comma N minus, okay, let me rewrite this. P N minus 2 minus P, H N minus 2G, minus H N minus P minus 1, and here P plus 1, sorry, H and G. Okay, there is a correction term. The bad thing is that in general, this second term is, okay, this is terribly written. Let me rewrite it again. N minus P minus 1, P plus 1. Now, this subtraction actually has a geometric meaning, okay? You can look at the cohomology of D, and you look at exactly these Hodge pieces. So they should correspond if Poincare duality was true. But as these singularities might fail, and this subtraction is exactly the failure of Poincare duality. Okay, so this number has a geometric meaning. Okay, so now I wrote some numbers here, and let's put some concrete values and see what does this means. Okay, so let's do the case of surfaces n equals to 3. So in this case, we have weight 1, weight 2, and weight 3. Okay, so we had said that the adjoint is I0 weight 1. We want, if you made the new one, I0 weight 2. And we have I0. This is the last step. Okay, so the corollary is that the first two coincide if and only if all components, okay, so n equals 3, this is a surface, the exceptional set is a curve, so it's a bunch of curves intersecting, and then this is an equality if all of components are rational curves. Or in other words, the contribution of the difference comes from the genus of each of the irreducible curves that appear in this simple number crossing divisor. And the second part is that associated to G, so again, G is a curve, we can associate what we call the dual complex of G. So this is going to be a graph whose vertices are irreducible components and edges are intersections. And then we can interpret the second relation, I0 weight 2D is I0, if and only if this graph has no cycles. Okay? In other words, the contribution from I0 to I0 weight 2, like that jump, corresponds to the first cohomology of a graph, which is captured by the number of cycles that appear in this graph. And this is going to be true for higher dimensions, okay? But let me not write all of these. Okay, so this is basically the picture in low dimension for I0. And this can be generalized if you understand, if you have a resolution of singularities, you understand the exceptional divisor, then you can compute the jumps. Okay, so that's the moral of this thing. Any questions? Mm. So, I mean, I have tried. I think that the main issue is that this result I'm giving is for isolated singularities, right? So this is capturing the isolated singularities. Like the main big step I'm hoping with this project is to like give the jump to higher dimensional singular locus. And I think the issue is that in many of these moduli spaces, I don't know, I think you get in the boundaries semi-log canonical singularities, which might not be normal, and then you will need to be able to say something about one-dimensional singular locus. So yeah, about that, I don't have anything to say yet. But that's a natural step. And I'm going to be more precise about exactly what's the issue probably at the end of the talk. It's not that we cannot say anything about high dimensional singular locus. It's that there are a few things missing. So yeah, probably that will be the last part of the talk. Okay, so now let me just say a few words and try to answer something that Hussein was saying. Is like, what are these? Like, is there some way of describing them in some sense? So for this, let's say that f is, I mean, let's say we're studying this locally, so that a function defines d, and the trick here is that we take the graph embedding of x to c, graph embedding, and in some sense, you can study this sheaf, the push forward on x plus c. And the nice thing is that now to define a V filtration, you need a smooth hypersurface. And here, by taking the smooth hypersurface given by, if you call the variable on C, let's call it t, making t equals 0, you're exactly capturing the the support coincides with the one of OXRD. So in some sense, this is the correct sheaf to study, and there's a concrete description. This is, you just need to tensor over C with a what you call the partial derivative with respect to t. This is what the d modules push forward would be. Now, associated to these d modules along a smooth hypersurfaces, you can associate the V filtration. Okay, so you can associate a V filtration. So this is probably, I don't know, this is a parenthesis, a bit more for experts, but this is like what you will require to give a concrete answer, a complete answer. But let me just write it for the sake of completeness. What this says is that if you have this description for the V filtration, then you can actually say what are the elements using this formula. You take j equals 0 up until p, where p is the degree of the Hodge ideal. And then I'm going to explain in a second what is this qj. Fp, f is the function here, and some vj's, where these vj's are exactly these. So this goes until p, vj's, delta t, j's delta, in v1 of I plus ox star d, ox star. So if I write only this will be exactly the description of Hodge ideals with no L in the picture, okay? And now to put this in the picture, this has a nilpotent operator, which is delta tt minus 1. So what you require is that V is in V larger than 1, or that if you take GER of V, these parts are the ones that have a nilpotency index of at most L. This is exactly the weight Hodge, the IP weight L. So it's not terribly illuminating, but j minus 1 equals 0. Okay, so this is the formula. So again, this is not terribly illuminating. This is the correct answer in some sense, but now you need to give a description of the V filtration. And this has also been used by Popa and Mustatsa to, for instance, give the description when D is not a reduced divisor but a Q divisor. You can use a very similar formula. And okay. So maybe here I should say for IPD, this is a result of Mustatsa and Popa. Okay, but I mean, let me say something with this formula at least. So if we have this xt, D has isolated singularities that are weighted homogeneous. So what this means is that it's given by a formula, and you can associate weights such that each monomial has weight 1 according to these new weights. So in this case, what you have is that I0. So the first result here is that I0 with 2 is I0. All of this is a result of Saito. It is described in the following way: is monomials such that if you take the dot product of this monomial plus the vector 1, 1, 1 with the weights of the singular, so weight is homogeneous, let's say of weight 1 until weight n, you take this dot product, then this needs to be larger or equal than 1. So these are the monomials that generate the zeroth Hodge ideal. And if instead you look at weight 1, then it's very similar. It's monomials such that this dot product W is strictly larger than 1. Okay. So in some sense, this is the complete description of the zeroth weighted Hodge ideals for weighted homogeneous singularities. Okay. And now the result of Saito, this is all Saito. It goes deeper. It's not only that we can say I0, we can also say all of the IPs by a formula of, for instance, if you want to look I1, so there will be a piece that comes from monomials such that this dot product is larger or equal than 2. And then you need to add, basically you put these monomials divided by f, and you take partial derivatives. So there are things divided by f squared, and whatever you get on top, those are also the contributions. So you add those with the ones with dot product larger or equal than 2, and that's I1. And then you can keep doing that for all p's, and the same for weight 1. So truly, this gives a complete description of all weighted Hodge ideals in the case of weighted homogeneous singularities. Okay.
As far as I remember, this V has to do with the monodromy around 0. I think that you have not completely defined, no?
It has to be. So the reason we only have up until weight 2, like the honest answer is that okay, so using the V filtration, you can define this is the way of defining nearby cycles and vanishing cycles, right? That's like the way of defining them using D modules. In this case, if you have isolated singularities, the vanishing cycles corresponds to the middle cohomology of the Milnor fiber, right? And then a result that follows from here, which was probably classically known, is that if you are weighted homogeneous, then the monodromy operator acts like 0. Okay, so the nilpotency index is 1. And as the nilpotency index is 1, that will tell you that you only have until weight n plus 2 in OX30. So yeah, that's what's going on here. Maybe another result I want to say. So this is a result that was okay. So let me write the result. Is that all of the Hodge ideals are contained in the adjoint ideal. This is a result of Mustatsa and Popa, but using this description that I give you with the V filtration, you get like a one-line proof of this fact. Okay, so this is giving that extra information. Okay, so I think I have like 10 minutes. So now I just want to talk about a geometric application. I want to introduce some terminology, and I want to finish with that. So it's like, okay, we have talked about isolated singularities with these Hodge ideals. Let's see what are they capturing and what can we use, what can we do with them. So, okay, let me go back here. Yes. No, the next one. Yes, this. Okay, so remember we have the picture of I0 weight 1 D contained in I0 weight 2 up until I0. So I gave you the description of each of the jumps, but a known result is that if you add all of the jumps, Or in other words, if you put I0 mod the adjoint ideal, this gives you a vector space on the point, and the dimension of that is IHn minus 2 of G, like this cohomology of G, where this is, I don't know, you have G containing the tilde, the resolution of singularities of T. Another way of describing this is that this is the zeroth part with respect of the Hodge filtration of Hn minus 2. Okay? Now, the question is, when are these results known? Well, there is a case in which this is known. This is a theorem from Ishii, the 85. It tells you this: if, let's say we're looking at a singularity, is log canonical and not rational. So a way of saying this is if it is strictly log canonical, then Hn minus 2 GOG is 1. So this dimension is 1. What this means is that the quotient from the last one, by the last one by the first one, it's one dimensional, which means that you only have one jump, right? You start with the maximal ideal, and at some point you jump and have the trivial thing, and that's all you get. And she says that, and she called this, she gave a name. So suppose that h 0 comma s of hn minus 2 of g is different from 0, then we say that x in D is log canonical of type 0 comma s. So in this way, she gave a classification of isolated log canonical singularities using this Hodge theoretic invariant. And so let me just repeat this. What this is saying is that we start with I0D. So this is forced to be the maximal ideal. And then you have equality up until I0 weight L minus 1. Then you have this jump at I0 weight L, which is forced to be OX. And then you just have equality up until I0 OX. So we knew that I0D was OX because they are log canonical, right? And if you remember, if I0 is trivial, that is telling you that the singularity is log canonical. But in some sense, this is capturing that jump that appear in the name of EE in Ishii, right? And some examples are known classically. These are like classical classifications. If n equals 3, so we're looking at surface singularities, surface log canonical singularities, then we have two types. We have either 0, 0 or 0, 1, okay? And these are known. This is called simple elliptic. So what this means is that the minimal resolution of the surface has a smooth elliptic curve, okay? And the other one is called cusps. So what this is saying is that if you take the minimal resolution, and let's say that now you require that they are smooth, like every component is smooth, what you get is exactly how you call this, a cycle of rational curves. Okay, so you have one cycle. So if you remember, these are the only two possible ways in which you can have one: either an elliptic curve, which gives genus 1, or one cycle. Okay, so now to end the story, so there's a result I can say in this sense, but I want to end the story with the following. Saying that, okay, so let's call this associated to F. We have the Bernstein-Sato polynomial. We have the reduced Bernstein-Sato polynomial, which is the division of VF plus S plus by S plus 1. And we call the minimal exponent, alpha L, is the negative of the largest root of BFS. Okay. So in some sense, this is like a refinement of the log canonical threshold. So if you have the low canonical threshold of xt, this is the minimum between 1 and alpha tilde f. And this is in general a very, a very well studied, how you call this? Okay, number associated to the singularity. Now, x in D is log canonical, not rational. So saying this sentence, you are log canonical, not rational, is exactly the same as saying that alpha f at the point is 1. Okay, so alpha tilde is larger or equal than 1 if you are log canonical. Alpha tilde is strictly larger than 1 if you are rational. So saying strictly log canonical is saying that this equals to 1. And then one result I have is a similar picture. It tells you that suppose you, instead of having alpha tilde being 1, suppose that you have, x isolated singularities, and you have that alpha tilde is p plus 1. Okay, so an integer, right? Then the result, what Ishii proved in the case of I0 is true for IP, which is another way of saying is that this is the maximal ideal. Okay, and let me add here that alpha f equals p plus 1 automatically implies that IP of D is trivial. So you have the same picture at every level. You start the maximal ideal, you keep going, at some point you have a jump, and then you have the whole thing. So what this means is that, I don't know. I give this definition with the blessing of Ishii, is that if you have alpha tilde is p plus 1, and suppose that you have fn minus p hl is exactly the one that is not 0, so x is p log canonical of type p comma n minus l minus p. Okay, so this is just, I know I went into some deep terminology of the modules, but this is just the same analog of the result of Ishii in the case p equals to 0. Okay, and now the final the result I want to give is how to use, how to obtain geometric information. So the result is the following. Suppose we have a hypersurface of Pn, reduced hypersurface of Pn of degree d, of degree d, with at most isolated singularities. And then you also assume that the pair PND is P log canonical. Okay, so P log canonical is a generalization of being log canonical, right? Log canonical was that I0 was trivial. P log canonical is that IP is trivial. Okay, so let's say you call Z the union of strictly P log canonical points. So these are the ones where the minimal exponent is P plus 1, and you call Z2 the union of strictly P log canonical points of type. So the lowest type you can have is P comma P. This is a result also of the monodromy of the Milnor fiber, up until you exclude the last one. Okay, so the top one is n minus 3 minus n minus 2 minus P. So this is, you exclude the last one, and then the result is that you can count these points. This is the geometric application. So the cardinality of Z2 is smaller or equal than this number, P plus 1, D minus 1, n, and here you have that this is P plus 1, dn. So in the case of I0, what this is counting is Z2 here will be counting the number of cusps that a reduced surface of degree D in P3 can have, right? And well, the other one would count the number of low canonical points, which in low dimensional, you can use geometry to get better, sharper bounds. But in the case of the cusp, I think there were not like good bounds no good ways of bounding them in a low canonical pair. So this is like you put together, you prove some vanishing theorems. You conclude with the fact that as IP weight 1 is maximal ideals, so these weighted Hodge ideals are actually counting them, right? Because they're counting them with multiplicity 1. And then taking advantage of that is that you can get this bound. Okay, just let me now end with a final result, which is what I was answering to Roberto, is what happens in the higher dimensional singular locus case. So this result that is analog to what you have for multiple ideals and for Hodge ideals basically tells you that you understand the picture generically. Okay, so what is this? X is a smooth variety, the effective divisor as always. And now suppose that H is a smooth hypersurface with the following conditions. First, that H is not contained in the support of D. And second, that if you call this DH, which is the restriction of D to H, is reduced. So if this is satisfied, then you can ask how to compare. So on one side, you have now the weighted Hodge ideal of the divisor DH in H, and on the other side, you have the Hodge ideal of D, right? And a natural way is to compare the restriction of IP weight L with the other Hodge ideal. So the result is that this is always contained. And if H is general, we have equality. Okay. So what you can do is basically suppose you have a one-dimensional singular locus, right? So what you could try to see is like to understand the rank of this coherent sheaf. Then you cut it with a general hyperplane section. Now in H, you're only going to have isolated singularities. Okay, so those we understand. We look at the resolution, we look at that dimension. So that will give us the rank, like the generic rank. And in general, you can keep cutting if you have a higher dimensional singular locus. Now the issue is there are some points in a one-dimensional singular locus that a general one will miss, right? Like these special points, like the zero-dimensional strata in a Witten stratification. So those are the ones we still don't understand. Like these kind of points, and if you have higher dimensional singular locus, there are analogs of these points. So those are the ones we'll still don't understand. And I think this is a good point to stop.
Okay. I'll stop recording just a moment and then ask questions.